Magnets can be classified as either permanent magnets or electromagnets. In this video, we'll explore electromagnetism, the phenomenon where electric currents generate magnetic fields, and see how this works in wires, coils, solenoids, and electromagnets. Let us start with exploring the magnetic fields around a straight wire. When an electric current flows through a straight wire, it creates a magnetic field around the wire, represented by concentric circles. The field is strongest near the wire and weakens as it spreads outward. The direction of the magnetic field depends on the direction of the current, which can be determined using the right-hand rule. Point your thumb in the direction of the current, and the curl of your fingers shows the field direction. For upward current, the field is counterclockwise. For downward current, it's clockwise. Next, let's look at how the magnetic fields change in a simple coil. If the wire is shaped into a flat circular coil, with current entering one side and exiting the other, the concentric magnetic fields from each side interact. This interaction stretches the fields into ellipses, forming a single magnetic field that passes through the coil's center. Adding multiple closely spaced turns to the coil creates a solenoid. Inside a solenoid, the magnetic field is strong and uniform, while outside it creates ellipses resembling the field lines of a bar magnet, with a north pole where field lines emerge and a south pole where they converge. This setup effectively creates a magnet powered by electricity, hence calling it an electromagnet. Electromagnets are only magnetic when current flows through them. Electromagnets possess several important properties. One key property is control. The magnetic field is generated when an electric current is turned on and disappears when the current is turned off. Another notable property is reversibility. Reversing the direction of the current causes the magnetic field to reverse direction as well, which also changes the polarity of the electromagnet. Let us take a look at how we can strengthen an electromagnet. The issue with a small electromagnet, like the one illustrated here, is that it would produce only a very weak magnetic field. To address this, there are four key ways to increase the strength of an electromagnet. The most straightforward method is to increase the current flowing through the solenoid. Another approach is to increase the number of turns in the coil, while keeping the solenoid's length constant. Alternatively, reducing the length of the solenoid while maintaining the same number of turns can also strengthen the magnetic field, as electromagnets with densely packed coils are the most effective. Finally, inserting an iron core into the solenoid can significantly amplify its strength. Iron, being a soft magnetic material, becomes magnetized when the solenoid is active, greatly enhancing the magnetic field. However, it is important to note that the iron core will lose its magnetism as soon as the current is switched off. Electromagnets play a significant role in various aspects of everyday life, with an induction hob being a fascinating example of this technology in cooking. An induction hob features a ceramic plate under which an electromagnetic coil is located. When an alternating electric current passes through the copper coils beneath the surface, it generates a fluctuating magnetic field, but at this stage, no heat is produced. When a compatible pan, typically made from a magnetically responsive material like iron, is placed on the hob, the magnetic field induces small electric currents within the pan. Because iron is a poor conductor of electricity, these currents, known as eddy currents, cannot dissipate easily through the material and are instead converted into heat via a process called Joule heating. Unlike traditional hobs, which first heat the cooking surface and then transfer the heat to the pan, an induction hob directly heats the pan itself. This results in the hob surface staying relatively cool, making this cooking method both energy efficient and safer to use. In conclusion, we've explored electromagnets, their magnetic fields, and their application in induction cooking. We examined the magnetic fields and concentric lines formed around a straight wire, a coil, and a solenoid. Additionally, we discussed the unique ability of electromagnets to be switched on and off, as well as the capability to reverse their poles by changing the direction of current flow. We also covered various methods to strengthen electromagnets, such as increasing the current through the solenoid, adding more turns to the solenoid without increasing its length, shortening the solenoid to make it denser, or inserting an iron core into the solenoid. Finally, we connected this science to its practical use in everyday life, focusing on induction hobs and how they revolutionize cooking through electromagnetic principles.